Good morning, everybody. So, we were talking about the electrochemical methods of analysis, and as I told you that we will be basically talking about the electrochemical effect or electrochemical signals what we can find to determine some unknown analyte. It can be X plus or it can be Y minus, because always for us when we study analytical chemistry courses, always we must have some good idea about the identification first, then quantification of the species like X plus or Y minus. So, when we take the help of electrochemical methods, definitely we should go for some electron transfer reactions on cathode and anode as we are discussing. So, the species like these, the cationic species, we all know that in common water, what we drink, our drinking water, and we always very much concerned about the presence of sodium ion and potassium ion, because these two ions are very much important for our health, for our well-being. So, the concentration of sodium ion as well as potassium ion we determine basically in our drinking water or the bottled mineral water what we take. So, the problem to us should be how we determine the corresponding concentration of sodium ion and the potassium ion in mineral water. So, if we think that we can solve this problem by doing some electron transfer reaction on it, that means if you reduce it to sodium 0 and reduce it to potassium 0, then the problem will come that how will you go for the corresponding determination of the atomic state of sodium and the potassium. So, all these things are related for that particular type of analysis, where we know that the mineral water bottles is written with some amount of ppm values of potassium or ppm values of sodium as in the ionic form, because they are all mineralized. That means, the required quantity of sodium ion or the potassium ion is mixed with that pure water, which is only H2O. So, this would be difficult in that way for measuring the signal in terms of their electron transfer behavior, but we can go for some other technique. We know that we can use it by simple flame photometer to analyze this particular species. But today in this class, what we will be talking about is not that your sodium plus or potassium plus, because this anion is sometimes also very much important, because whatever salt we take as our table salt, common salt or food material, we all will be getting these as sodium chloride or potassium chloride. We are not taking these in some other salt, because we should have that question all the time, that why we are not taking any other salt of sodium or any other salt of potassium. Like for making food and all these things, we know that bicarb we use, which is sodium bicarbonate. Again you have the corresponding sodium salt, but the anion is bicarbonate, which we produce from in our body also when we burn the food material and we get the carbon dioxide. Now, the other one, that means the anionic counterpart, that means Cl and this Cl, whether we can determine this particular chloride ion concentration, forget about the presence of the corresponding cations like Na plus or K plus. But if we want to determine the total concentration of Cl minus in any fluid, whether we take as water or it can be your biological fluid in our body, in serum, in sweat, anything, as we know that this Cl minus, if we can little bit careful about thinking the process of some electrode reaction, what we are discussing for many classes. So, the electrode reaction what we are thinking about, one such half cell reaction we have seen that is AgCl Ag plus. That means, the corresponding one when silver ions are there, so silver ions are getting, so is to Ag0. So, this silver ion silver 0, as we know the pure silver ion silver 0 electrode we know, but the other one is also that's silver chloride electrode, and this we all know that a very good RE, that means your corresponding reference electrode, we know the half cell potential and all this. So, in some way if we can have some good idea in any electrochemical method where the system can sense the corresponding chloride ion concentration, because making these half cells, what we have seen that certain amount of 0.002 molar chloride concentration was required for making that particular cell. So, you see this particular concentration and the cell potential, the corresponding E0 value for the half cell is dependent on the corresponding concentration of this chloride. So, in any way we can have some idea or clue that we can manipulate the process for tracking the corresponding presence as well as the concentration of the chloride in any fluid. It is possible then. The determination of chloride concentration in any fluid, and we will see that if it can be a typical biological fluid. So, how we can see that? We can go for electrochemical method, and that electrochemical method is a typical one where we can consider it as coulometric titration, because the chloride can be handled in all different types of titrations. Particularly we know that since we are talking about this Ag plus, so if you have the corresponding unknown chloride concentration which is unknown, we want to determine the unknown chloride concentration. We can have AgCl which precipitate out, and we know that one such titrametric method is the precipitation reaction like your neutralization reaction or redox reaction or metal ion complexation reaction. So, this particular precipitation reaction can also be useful to determine this Cl minus, but why you should go for any electrochemical technique to determine this Cl minus, that is the most important question to be asked, because this concentration, because for a meaningful precipitate, if you want to have, if you want to see or locate it by addition of some indicator, what we should know that this concentration, this is also a very low concentration. So, these concentrations are 0.2 or 0.02 something like that. So, this higher level of concentration, so which is 10 orders or 100 orders of magnitudes higher concentration than that concentration what we find in the corresponding electrochemical cells or what we can apply for any electrochemical method. So, when your concentration is high, what you can do, you can go for this corresponding precipitation titration, but if the concentration is low, we cannot go for this. The thing is that as we go down to a concentration, because we know that 10 to the power minus 3 molar to 10 to the power minus 5 molar concentration is good and very easy to handle, not for your typical analytical methods using different titrations. So, these are useful for your spectrochemical methods what we have seen earlier. So, in spectrochemical methods, now if we go down further, that means 10 to the power minus 5 molar to 10 to the power minus 7 molar, what we should do? We should go for sometime this spectrochemical method using UV visible spectrometer. We can go here simply the fluorometric technique. The fluorescence we can measure. At the same time also this concentration we can handle for electrochemical methods of analysis. So, we see now that a titrametric method which is based on coulometry, that means we can measure the corresponding coulomb count or electrical charge count for a typical titration when chloride is the anion in any biological fluid. So, that will be a very good example for utilization of electrochemical methods, because this is typically a introductory class for you where we can introduce the thing that how we can move from a typical electrochemical methods or electrochemistry to a bioelectrochemical process. That means, how we can apply to different biological problems or determination of the corresponding concentration in different biological fluids. So, starting from blood serum to plasma to sweat, urine and any other body fluids if we have, because always we have either sodium chloride or potassium chloride, we get it from direct salt or we get it from any food material. So, anion, the most prevalent anion apart from the sulfur based or the nitrogen based other anion, chloride is the typical anion. So, the suitable procedure is your electrochemical method, and that electrochemical method not by voltammetry, not by potentiometry, it would be on coulometric method. So, coulometric titration procedure would be useful in that way. So, how we do that? Again we can do that. The silver ions application, that means this is the fundamental information, the fundamental knowledge you should always have, that whenever is problem is with silver ion, you think of chloride. Whenever it is for chloride ion, you think of the corresponding silver ion. So, silver ion is generated coulometrically. So, if we generate silver ion coulometrically, that means the number of electron transfer taking place for the required number of silver ions to be produced in solution is known by the coulometric charge count or the Coulomb count, which can react with the available chloride ions such that it can immediately react to give you the silver chloride precipitation or electrical sense, because these two are combining for a half cell reaction, which is your Ag plus AgCl half cell electrode, because we know the potential and also we can find out the corresponding change in the concentration with respect to your chloride concentration. So, when we go for amperometry, so this is the new terminology, what you right now you can just listen and try to remember it, because it is related to ampere, is related to coulomb is coulometric titration. If it is related to amperes, it will be amperometric titration. So, in amperometric titrations, as I is known from the name itself that it is ampere, that means the current. So, if we can measure the corresponding current during the titration, what we measure for potentiometric methods, the change in the potential values during titrations. Now, we can measure the corresponding change in the current in terms of several amperes, because it is not several amperes, it is several milliamperes, microamperes or nanoamperes as we go down, down, down. So, what that electrical sense mechanism, that electrical sensing mechanism is known to us from 10 to the minus 3 to 10 to the minus 5, then 10 to the minus 5 to 10 to the minus 7, and then again 10 to the minus 7 to 10 to the minus 9 molar can be handled in terms of the corresponding current, the amperes. So, this ampere we will see that routinely we can use as the microampere, we can use it as the milliampere, or we can use it as nanoampere. So, as we go down, we can have some information or the corresponding electrochemical transducer, which is amplifying the signal what is coming out from the electrode reaction, because you have the electrode and that electrode is responsible for giving you the corresponding reading in terms of either voltage or in terms of the corresponding current. So, milliampere to microampere and then microampere to nanoampere you can tackle or you can handle, because these are all concentration dependent. At certain concentration you get a current of milliampere range, in other case you get a current in the microampere range, in other case you get, or you can go down to a nano level, which is a nanoampere range. So, the detection of this current by this amperometric method is useful when a sudden increase in current occurs, that we have seen also earlier, that what is there, that is sudden change during the end point we get certain change. In case of your potentiometric titrations, what we have seen that the potential is changing and there is a sudden jump. So, the staircase like or the integral type, sometimes we call is as the integral step, that integral stepped curve. So, this integral stepped curve will tell us that a sudden change. So, you see that this particular change only few drops only. So, this is the change. So, this is your E0 axis and this is your volume. So, this volume is very small, this volume is very small. So, as we always know that with a drop of titrant, when it is colorimetric with a drop of titrant at the end point, there is a color change, sudden color change from say color to colorless species or one color to the other color. So, this particular one will also give you the idea that you have a sudden change. So, sudden increase in, now we are talking in terms of sudden increase in current I. So, it can be in any unit, it can be milliampere, it can be microampere or it can be nanoampere, but we should be able to plot it. So, this plot will tell you that there will be a sudden increase in current occurs on the generation of the corresponding species like your silver ion. That means, generation of slight excess of silver ion, there will be that particular current change that will affect your corresponding potential as well as the current which is being traversed. Because why you have the slight excess of silver ion in the medium? Because your chloride has all been exhausted. Whatever chloride ions you had earlier in these biological fluids has all been consumed. So, that is the typical process what we follow for any titrations or any titrimetric method, is that the silver ion will be now excess because we are titrating everything with the silver ion. So, chloride concentration is 0 because all the chloride has been consumed to form the silver chloride, and therefore, you have the corresponding sudden increase in current in terms of the corresponding ampere values and can be detected by the typical amperometric titration. So, the required amount of silver ion what you need for this sort of titration can be found out. So, which react quantitatively with the Cl minus is found from the Faraday's law. How much you require depending upon the corresponding charge and the current, we can use that can be useful from the well established Faraday's law. So, that basically tells us that how you can go for the typical technique which is your voltammetry. So, as we have seen that earlier we used that corresponding one, that the Faraday's law for the typical reactions where we can find out the corresponding charge in the coulometric processes. Now, we can go for the voltammetric method. So, voltammetry, like not like your potentiometry, but you have now voltammetry or voltammetric methods of analysis. So, you should immediately know that we are talking about something where these two terms are there, one is volt and another is ampere. Voltage versus ampere is there, therefore, we have always we have, if we get the plot, the current potential curve what we are looking for. So, the output of this particular technique, the voltammetric methods of analysis will give rise to a corresponding current potential curve for any electroactive analyte. So, the analyte should be electroactive. That means that species or the analyte what is there, it can go for oxidation or it can go for reduction. That means, analyte if we consider it can be oxidized or analyte it can be reduced by taking electron or by losing electron. Okay. So, if it is there, we can get a particular methodology what will be called as the voltammetric methods of analysis, and there are different things. That means, we will not find any time for discussing once again the corresponding electrodes, but with the basic idea behind changing or the corresponding improvement of the electrodes compared to your potentiometric method, that we will discuss. So, a group of analytical methods. So, we are jumping on somewhere where not only a single method of analysis, but a group of methods we can have, and where we can get the information by measuring the current in an electrochemical cell. So, we will still with that electrochemical cell. Now, we try to measure away from your potential measurement, away from your Coulomb charge measurement. Now, we consider to measure the current as a function of applied potential. That means, your applied potential will not be now fixed, it will now be variable, and with that variation in the applied potential to the analyte, we will find out the corresponding current change with that particular process, and we will try to plot the current versus potential plot, which is your typical voltammetric plot, but the discovery way, the history way, the historical discovery has been made by Professor Herowski of Czechoslovakian origin, so who basically started all these things during 1920. For that, later on he got Nobel Prize also for that, and that particular time, this is a different one, is not considering as a voltammetric type of thing, but is a special type of voltammetry which is known as polarizography. So, we have the electrode, on the electrode surface you see either oxidation or reduction, and that can be monitored nicely with respect to the unknown concentration of analyte, which is giving rise to the corresponding response of electron transfer. So, it is basically an excellent tool in diverse areas of chemistry, not only chemistry. When it applied to chemistry, we call it as analytical chemistry as well as the electroanalytical chemistry. When we will apply it to biochemistry, it will be analytical biochemistry or electrobiochemistry or bioelectrochemistry. For material science as well as engineering and the environmental sciences, because in any case, wherever we try to understand or try to find out the processes like oxidation, the processes like reduction, or sometimes the adsorption processes. So, these three things basically together, initially we will discuss about the oxidation or the reduction reactions, then finally we can think of the corresponding adsorption processes, because we know now that why you have the adsorption related to these sort of processes, because we can have, just now we have seen that you can get silver 0 to silver ion, and when it combines with chloride ion, you get the corresponding formation of silver chloride, which is a precipitate we know, since soluble in aqueous medium, having a certain magnitude of solubility product. So, if you exceed the solubility product, that means the individual multiplication of the concentration of these two ions, you get the corresponding precipitation. So, this when initially form, when at a very low concentration it is forming, it can form a film like material, and as we know that this film like material, and we are talking about something where you have the thing that you can have, that corresponding one is the electrode. So, we are talking about electron transfer on electrode, and we are talking about some solution, and this is forming in the electrochemical cell. So, it is surrounded by this particular electrode. So, you can have a very thin film of these materials can be deposited. So, once they are deposited as a film on this electrode, and if these are considered for the corresponding adsorption, so we can study the adsorption processes as well. And the very simple idea how you apply your idea for that, because if you know the corresponding deposition, as we know that the coulometric deposition on the electrode surface of the metallic state, that means when copper is deposited from copper 2 plus or cadmium is deposited from cadmium 2 plus as the metallic species, we know that the deposition will increase the weight of the electrode, and we take the corresponding weight and we find out the corresponding weight difference, that means the delta W for the amount of deposition related to the charge transfer. Now, if any other material is also deposited on the film, that we can find out, and also the species, that means what is being deposited on the electrode as a film is also electroactive, because you can go back again to your silver 0, because it is starting from silver 0. So, if we can go back to silver 0 or any other species like that, that means during that particular electron transfer reaction, the material can be leached out, can be removed, can be eliminated from the electrode surface. That means this particular type of adsorption as well as the dissolution process from the electrode surface can also be monitored. So, this oxidation, reduction and adsorption processes can be monitored by means of this polarizographic technique, or the most advanced one is your voltammetric technique. So, during this particular process, that means the voltammetric process, what we use the different excitation signal, because why we get, because we will be Moving towards something, the process is known as cyclic voltammetry. Why we are bringing another term which is cyclic one, is not a linear sweep. So, a cyclic sweep and linear sweep, all these things are related to those things, but particularly you should know what are the excitation signals. That means the excitation signals, how you put the corresponding potential. So, a variable potential which is used for your excitation, that means for your electroactivity, is allowed to get on the working electrode, that means WE we call, in an electrochemical cell. This excitation signal produces characteristic current response. So, when you put the potential depending upon the signal, because nowadays most advanced instrumental techniques and the computer controlled instruments also can give rise to all these advantages, because most of these advantages are based on the development for the different computers and the corresponding instrumental parts basically, which is a measurable quantity. So, the current response we measure as we put the corresponding voltage as ramp say. So, if you have a typical waveform, how we call it, so is a linear scan. So, some will be considered as the corresponding cyclic one, as I told you. So, if you have the linear scan one, so this linear scan voltammetric process is that now we will be considering with respect to time. So, how your potential is changing with respect to time. So, E is linearly increasing. So, waveform looks like this. So, we get that for a linear scan voltammetric type of thing. So, you have the corresponding polarography. So, technique what we get from linear scan waveform is polarography and hydrodynamic voltammetry. So, these are the two processes. So, that is why polarography is the oldest technique, is almost 100 years old now. So, this 100 years old technique, but it has the origin for that type of waveform. Now, once you know that the linear sweep voltammetry or the linear sweep polarographic method can be useful for this sort of analysis, you can apply that to the change in the corresponding waveform. So, if you have a differential pulse, that means the differential pulse is your corresponding delta E versus time, delta E delta t. So, d by dt, that particular form. So, it looks like this. So, you have the, at this particular point you have the corresponding pulse, and this corresponding one that is also linearly increasing, and the when it is coming back to this level, this is also increasing linearly, but the waveform is little bit different from that of a RU. So, at this point you have the corresponding pulse is the differential pulse. So, if you give this differential pulse to the system, your nature of this plot will be different. So, the type of voltammetry what we get is your DPP, is the differential pulse polarography. So, originally when it is linear one you have polarography, and when it is a non-linear one, a differential type of thing, we get the differential pulse polarography. So, in a same fashion, when we will be seeing the voltammetric technique, it can be a cyclic one also, and this can also be at that point will be differential pulse voltammetry, which we call as the DPV, because nowadays these are all very routine, because the oldest one historically these are all important, but the improvement, the techniques what is getting improved, and the convenience of the process is increasing day by day. It should be very useful, and the size of the electrode, particularly the electrodes which are going to the micrometer size, we call they are micro electrodes, but earlier we call the smaller electrode as the micro electrodes. So, the development not only in terms of the electrode development, but the electronics, the instrumental part, as well as the ease of doing the operation, that how quickly you can do or how quickly you can measure, because sometimes we can call it as in situ or ex situ. That means you can do immediately, if you have a solution you dip the electrode and measure it. So, these two are not useful nowadays, because the polarographic technique is useful for the electrode type is the corresponding hanging mercury electrode, which is HME, that means dropping mercury electrode. So, that dropping mercury electrode had some earlier advantages which has now been removed, but handling a dropping mercury electrode is not very much useful, not very much handy, because from the environment concern also the hanging dropping electrode is discarded. That is why we are slowly moving from one technique to the other, and we move to the voltammetric technique. So, when you have the square wave one, the previously what we see is the differential plus, but is linearly increasing from say like this linear scan. But when we get square wave is also changing, but the wave is typically a square of this time, and the nature of this wave is different, and we get the corresponding one is known as square wave voltammetry. So, depending upon the wave form what you have, the name of the technique is also leveled with respect to that. So, if your waveform is square wave, it will be termed as square wave voltammetry. If it is triangular and cyclic one, it will be cyclic voltammetry, because the triangular waveform what we get, potential is moving from here, is reaching some point, and then it is coming back again to the original level. But your time has elapsed, that means this point is not coming to here. So, with respect to E, so with a time cycle, that means with second, if you are able to scan a corresponding potential, that means certain amount of millivolts, say 500 millivolt, if you are able to scan within a second. So, you have a scan rate for that. So, 500 or 100 or even 50 millivolt, which is the slowest possible scan rate. So, you have with time. So, this is if this is a second scan. So, what you do, that means if it is 50 millivolt per second, so half of the second it goes to 0 to 25 millivolt, and then again it is returning back to the corresponding voltage again to 0. So, this triangular waveform is giving rise to the birth of a cyclic voltammetric technique, and that we will see how useful this technique is and is a most convenient one. So, these waveforms should be generated by different voltammetric instrumentations, and these instrumentations are depending on the working electrode, their dimensions, as I told now just, that you can have the micro electrode, the smaller electrodes, and they all kept small to enhance the tendency to become polarized. That we have seen earlier, that the polarization effects are there when the size of the electrode is more, and the RE is the corresponding reference electrode, and it has a potential that remains constant throughout the experiment. So, how should I do that? Because since we are considering some reference, the reference electrode can be considered as a reference material, and with respect to that reference we are measuring something. We will be measuring the working electrode potential also, and if something else is also there which can also be monitored with respect to that reference electrode. So, this should be constant, and how you get that constant reference electrode potential? If you do not allow to pass any current through this reference electrode. So, we must have some alternative arrangement that we should not allow to pass any electron through this reference electrode, and this will remain constant throughout your experiment. That means, throughout the time period within which you are doing all these experiments for your measurements. So, the most latest type of these instrumentation, that is the voltammetric instrumentations, the excitation signals, these signals we generate electronically, and definitely these are all computer controlled. That is why, and these computer control and electronically generated waveforms will give rise to the corresponding measurements only. And what we do is that the potential in a systematic way we vary or we change, and with respect to the reference electrode we record the resulting current. So, that is the most important thing, that how you follow the thing, that you bring the reference electrode, and the reference electrode will say us and will give us the values what we can put on the working electrode, and with respect to that we now record the corresponding current what is being passed through the electrochemical cell for your plot of your current potential plot. So, that we will see in our next class, that how we can continue with that, how we measure and how we get the corresponding current potential curve for this measurement. Okay, thank you very much.